Arrange an immense data set in a logical order. This single operation is one of the strictest performance bottlenecks in computer science. Execution speed is not an accident of hardware. Time complexity, how an algorithm's runtime scales as input grows, is a rigid mathematical output dictated entirely by a programmer's structural code choices. This graph plots the three primary complexity limits that govern all sorting algorithms. We have the quadratic boundary, expressed as big O of n squared. Below that, the log linear boundary, at O of n log n, and finally the linear boundary, at O of n. Big O notation is a mathematical shorthand used to classify how an algorithm's runtime requirements grow relative to the input size. Moving an operation from one curve down to the next requires a change in the underlying logic of the code. We are going to deconstruct the specific Python syntax behind these algorithms to prove how distinct loops, recursive functions, and memory mappings directly force execution time into these strict mathematical boundaries. Identifying how a specific code structure determines these mathematical limits allows you to predict software performance before the program is even run. We begin with the comparative baseline models, bubble sort and selection sort. Both algorithms rely on a shared core mechanism. They operate via contiguous, element-by-element comparison. This split-screen diagram illustrates the structural bottleneck in Python's implementation of bubble sort. Look at the code on the left. The architecture relies on nested loops, a primary for I in range loop, which directly contains a secondary for j in range loop. When you nest loops like this over an array of length n, the mathematical consequence is a multiplication of effort. Every single element is subjected to a comparison against every other element, generating a massive grid of redundant operations. This structure traps the algorithm within a specific boundary. In both average and worst-case scenarios, the execution time is strictly locked at O of n squared. Selection sort approaches the task differently, by scanning for the minimum value rather than bubbling up the maximum. However, because it relies on the same nested loop architecture to scan the list, it suffers the exact same O of n squared limitation. To escape the quadratic trap of n squared operations, engineers must abandon the architecture of contiguous element-by-element scanning completely. Breaking the n squared barrier requires a new structural approach, the divide-and-conquer architecture. This tree diagram maps the core logic of merge sort. Instead of scanning the full list sequentially, merge sort divides the initial array in half. It repeats this division until it isolates single elements, which by definition are already sorted. By cutting the dataset in half at each step, this recursive architecture bypasses thousands of redundant comparisons. The total depth of operations shrinks mathematically, compressing the execution time boundary down to O of n log n. This speed carries a strict architectural cost. Merge sort requires an O of n space complexity to hold the newly divided sublists. Space complexity is the total amount of working memory an algorithm needs to execute. Quicksort offers a comparative alternative. Rather than executing a memory-heavy halving process, it utilizes an internal partition procedure. This visualization shows Quicksort's partition function in action. The code selects a specific element as a pivot. Pointers I and j move inward from opposite ends of the array, swapping values to physically separate the list into elements greater than and less than that exact pivot value. The quicksort function then recursively calls itself on those newly separated halves. This partitions the data continually, mirroring the logarithmic depth we saw in merge sort. There is a flaw in this architecture. If the initial dataset is already sorted, Quicksort's pivot selection fails to divide the array evenly, and performance collapses back into the O of n squared worst-case scenario. On average, however, it maintains the target O of n log n. Recursive partitioning breaks the quadratic limit. Yet, merge sort costs too much memory, and quicksort carries a severe worst-case risk. Therefore, a perfect structural compromise is required. The flaw of merge sort is memory allocation. Creating distinct new subarrays for every single recursive division taxes system memory. Heap sort provides the solution. It operates entirely in place, modifying the original array directly while securing the optimal O of n log n time efficiency. This diagram illustrates the heapify procedure. It structurally maps a flat one-dimensional list into a logical binary max heap tree. It achieves this without allocating new memory by applying strict index math. The script calculates a node's parent with the formula I-1 floor divided by 2. It locates the left child at 2 times I plus 1 and the right child at 2 times I plus 2. The execution phase happens in 2 steps. First, the algorithm converts the list to a heap in O of n time. Then, it isolates the sorted list by performing exactly n minimum delete operations. Because each deletion travels down the tree, each takes only O of log n time. Heap sort proves optimal comparative limits are achievable without a spatial penalty. This specific code structure represents the peak of the comparative sorting paradigm. This leads to a specific technical challenge. Can we bypass the O of n log n limit and sort data in linear time? This is possible only if we abandon the logic of element-to-element comparison completely. This is the domain of non-comparative architectures, spearheaded by counting sort. This diagram shows the non-comparative mechanism. The code generates a separate auxiliary array, defined as C, scaled to the largest number in the dataset. As it iterates through the input, it maps each value directly to its matching index in array C, tallying the occurrences. No 2 input elements are ever compared against each other. Look closely at the trade-off. Linear execution time requires massive spatial allocation. If you need to sort a list containing the number 1 million, array C must generate 1 million empty indices just to hold it. If the integer range of your input data is vast, counting sort becomes unviable. The memory demands will crash the system. Radix sort is the structural mitigation designed specifically to solve counting sort's memory problem. This visualization demonstrates radix sort's key factory logic. Instead of mapping an entire integer value, it processes numbers digit by digit. It uses base 10 math, dividing the number by the base to the power of the digit position, and applying the modulo operator to isolate exact ones, tens, and hundreds columns iteratively. By focusing on individual digits, the script limits the size of the required auxiliary array to exactly 10 indices. It runs the counting sort logic multiple times, but saves significant amounts of memory. The linear time limit proves that time and space are a zero-sum game. To achieve absolute speed, you must pay the toll in memory. These sorting algorithms function as a toolkit of architectural trade-offs. This chart maps the 3 overarching archetypes. We have the n-squared loops, which are slow but highly memory efficient. We have the n log n recursive tree structures, offering optimal comparative speed. And we have the linear non-comparative logic, providing absolute speed at extreme spatial cost. You also have specialized optimizations, like shell sort, which utilizes a calculated gap sequence of 2 to the power of k, minus 1. Tweaking these spatial gaps yields specific middle ground efficiencies between the primary curves. Ultimately, there is no universally perfect algorithm. Selecting the right code is an engineering decision constrained by the limits of your hardware. You must determine if your specific system is bottlenecked by execution time, by memory caps, or by the initial entropy of your data. True mastery of data structures requires moving past code memorization and visualizing the mathematical shapes those loops, recursive trees, and memory mappings carve directly and permanently into the underlying system itself.